Hello, so welcome everyone. I hope you can hear me and can see the screen of our shared screen of our today's speaker, which is Professor Anton Burkov. Very happy that he will speak to us today. I think this was also the date of his original invitation to visit us, so at least it worked out in the end. So let me introduce our speaker today. So Professor Burkov is a full professor at the University of Waterloo in Canada. He received his PhD with Alan MacDonald in Indiana, so not too far from Ames. And then he did postdocs at UC Santa Barbara and Harvard before joining the faculty in Waterloo, where he has been since, going through the ranks of assistant associate professor. Professor Burkov is very well known in the field of topological materials, particular topological semimetals, Weyl semimetals, Dirac semimetals, nodal line semimetals, and he has done a lot of work related to transport phenomena and optical phenomena in these materials. He's also well known for his work on the impact of electron interactions in topological materials and also non-topological materials. And I think probably he also worked on cold atoms before, since he was with Eugene Demler at Harvard, and I think I know some of his works when he was still working on cold atoms. He's part of our Center for Advancement of Topological Semimetals. That's this DOE EFRC, where some faculty members are part of. Me, Rob McQueenie, Paul Canfield, Adam Kaminsky, Lin Lin, and others. And so I'm very happy that Anton Burkov is speaking to us today, and he will tell us about topological metals. Just before I turn the microphone to him, let me say, I think we're going to do the same thing with the questions as we did last time. As far as I understand, Brad, our IT person, muted everybody. And so I think you have to use the chat box this time. And I will collect the questions and then ask it at some point during the talk, or collect some of them to ask in the end. And so I think let's try to make this as interactive as a regular colloquium would be, or at least we can all try. Okay, so with this, Anton, please go ahead. I'm looking forward to your talk. Thanks.
Thank you, Peter. Thank you for a nice introduction. Of course, it would have much better to be there in person, but this is better than nothing. So I'll talk about topological metals. So this is the outline of the talk. I will start with an introduction. What is a topological metal? Why are we interested in this? And then I'll talk about two groups of phenomena that are predicted to occur in these systems. I will talk about transport in weakly interacting topological metals, and then at the end, if time permits, I will also talk about some physics of strongly interacting topological metals. So, well, since this is supposed to be a colloquium, I guess let me start from afar. Let me start by asking the following question that any physicist, not just condensed matter, should be able to relate to, which is, where do gapless excitations come from? So, and let me illustrate what this means on the example of a sort of prototypical condensed matter system, which is liquid of weakly interacting bosons, which can, for example, represent a liquid helium. So in this case, if I completely ignore interactions, then the kinetic energy of these bosons is just p squared over 2m, right? And it's natural to count that from the value of the chemical potential mu. So then, suppose we are at some high temperature, and in this case, from your elementary stat-mech class that chemical potential of such a gas of weakly interacting bosons is going to be large in magnitude and negative. And this is because chemical potential is basically the free energy per particle, right? And at high temperature, the free energy is going to be dominated by this entropic piece minus Ts, and so it's going to be negative, okay? And so in this sense, the energy of all the bosons relative to the chemical potential is going to be high, right, at high temperatures. And in this sense, in this high temperature limit, there's going to be no low energy excitations in this system. However, again, as most of you probably know, if I reduce the temperature, the chemical potential is going to decrease in magnitude, and eventually there is a critical temperature at which the chemical potential goes to zero and crosses into positive values, right? And so what happens at this point is a phase transition into a superfluid. So the liquid of weakly interacting bosons becomes superfluid. And at this point, the excitation spectrum changes dramatically. So the excitations on all become collective, right? These are no longer individual bosons, but are phonons, right? These are collective density fluctuations, and they have a gapless linear dispersion, right? So the energy of these excitations goes to zero in the limit of zero wave vector. And so we know that the origin of this linearly dispersing gapless excitations is the phenomenon of spontaneous symmetry breaking, right? So what happens when you get a transition into a superfluid is that the field that creates this and annihilates these bosons develops an expectation value. It becomes just a complex number, and the phase of that complex number is arbitrary, and this arbitrariness reflects a conservation law, which is just the conservation of the number of particles, but this is spontaneously violated in the superfluid phase, and that's where these linearly dispersing gapless excitations come from. So something very similar happens in another prototypical condensed matter system, which is a crystal, right? So crystal is different from a liquid or a gas by the fact that the atoms in a crystal occupy a specific position in space. So therefore, crystal breaks translational symmetry of empty space. And as a consequence, the excitation spectrum of a crystal, of an insulating crystal, is actually very similar to the excitation spectrum of a superfluid. It also has gapless, linearly dispersing acoustic phonons. Okay? And again, it's a consequence of this spontaneously broken translational symmetry. Okay, so there are a couple of lessons that we can draw from these two simple examples. So lesson one is that so gapless excitations generally do not arise accidentally. There must be a reason. So a generic many-body quantum mechanical system is going to have a gap. It's going to have no gapless excitations. And lesson two is that the existence of these gapless excitations is associated with interesting physics, such as superfluidity, crystallinity, et cetera, and this is really the reason why I'm interested in that, why I'm interested in gapless excitations. Now, okay, so this was about a system of bosons. Now, the gapless excitations, I will actually be interested in is gapless fermions, specifically gapless electrons. And so the question of the existence of gapless electrons in materials is really the question, this fundamental question in condensed matter physics, which is when a given material is a metal or an insulator, right? And so we know that the sort of the basic physics of electrons in solids is determined by the following three principles. So the first principle is that the energy spectrum of electrons in solids has form of bands separated by band gaps, and this is just a consequence of basic quantum single particle quantum mechanics of particle in the periodic potential. Second principle is that electrons are fermions, and therefore they obey Pauli principle. So no two electrons can occupy the same quantum state. And the third one is that the number of states in a band is always twice the number of unit cells in the crystal. So, which is a consequence of the fact that the momentum space, unlike in free space, momentum space in the crystal is compact, and it's called the first brilliant zone, whose size is determined by the inverse of the lattice spacing. Now, it's a direct consequence of this that if we have a fractional, by which I mean not even integer, number of electrons per unit cell in our material, then some number of bands is necessarily going to be incompletely filled. So the Fermi energy is going to cross one or more of the bands, and then we get a metal. So in this case, we have a whole Fermi surface of gapless excitations whose volume is directly proportional to the number of electrons per unit cell modulo even integer. So this is a famous theorem due to Luttinger that this is basically an invariant that independent, for example, of interactions to a large degree. On the other hand, if the number of electrons per unit cell is even integer, then we get an insulator. So the certain number of bands is going to be completely filled while other bands are empty. And so there are no gapless electrons in this case, and this is an insulator. Okay. Now, this, of course, as many of you know, this is a little bit of an oversimplification. In reality, bands can overlap in energy like this. And so often materials with even integer number of electrons per unit cell fail to be insulators. So in this case, they become compensated semimetals where you have electron and hole Fermi surfaces enclosing equal volume in momentum space. So the kind of the net Luttinger volume which is weighted by the charge of the carriers is still zero, like in an insulator. Okay. And so another important point here is that there is nothing fundamental about the existence of this accidental compensated semimetal in the sense that this band overlap is really an accident of chemistry. So at least in theory, I can imagine changing some parameters, and then these bands are going to separate from each other, and you're going to get an insulator. Okay, so a genetic situation with even integer number of electrons per unit cell is an insulator. And well, just as before, so metals are interesting and useful. So they conduct electricity well, so you can make wires out of them. They conduct heat well, and we can make cookware out of them. They're ductile, and so we can make various materials for construction from them, and they're just shiny and beautiful. And all of this, to a degree, follows from the fact that they have gapless electrons. Okay. On the other hand, insulators have no gapless electrons, and they're boring. Okay, so of course, this is again an oversimplified statement. So if you are interested in insulators, don't take offense to this. But generally, I would say it's a fair statement that metals are more interesting and more useful than insulators. Okay, so now, this was kind of the standard picture of where gapless excitations come from. So they can come from spontaneous symmetry breaking, or they can come from filling. Now, so in the last few decades, we've realized that there is actually a third way in which gapless excitations can appear. And this has to do with topology. So basically, what we have found is that metals can exist on the surface of an insulator for topological reasons. And so, insulators are in fact not as boring as this picture suggests. There are in fact two classes of insulators. One that is really boring, that doesn't have any gapless excitations anywhere, and then the other class called topological insulators. They are gapped inside, but there is a metal on the surface. Okay. And so a natural question that follows from this is the following, and this has really been answered in the last decade and the last few years, really. So can bulk three-dimensional metals exist for topological reasons? Okay, or in other words, can I have a bulk three-dimensional topologically protected metal when the material should be an insulator by band filling, namely when the filling of electrons per unit cell is even integer. Okay. And so we know now that the answer is yes, and there are several different classes of such topological semimetals or topological metals that exist. So in this talk, I will focus on the one that was originally discovered and the one that's perhaps the most interesting and the most important, namely Weyl semimetal. So what is a Weyl semimetal? So Weyl semimetal is a gapless topological phase which arises genetically in three-dimensional materials that lack either time reversal or inversion symmetry. So which means that they're either magnetic or have non-centrosymmetric crystal structure. So what happens in Weyl semimetals is that so bands touch at a certain number of even number of discrete points in the first brilliant zone. And so ideally the Fermi energy exactly coincides with these points. And so unlike this accidental compensated semimetal, which I mentioned, which which exists which is really an accident of chemistry. The Weyl semimetal exists unavoidably, basically, as an intermediate phase between a topological and ordinary insulator in 3 dimensions. Okay. So, and well, the reason it's called Weyl is because if you expand the band Hamiltonian in Taylor series in the deviation of momentum from these touching points, it looks like basically the Hamiltonian of relativistic chiral fermions that come in 2 flavors corresponding to this sign in front here. And this sign is chirality, right-handed or left-handed. But let me not dwell on this too much. Okay, so let me now try to explain why this phase exists unavoidably as an intermediate phase between topological and ordinary insulator. So this is most easily understood in this situation when the material lacks time reversal symmetry, so it's magnetic. And so in this case, what happens, so the physics here is really the transition between a 3-dimensional integer quantum Hall insulator and an ordinary insulator, okay? And the nice thing here is that this situation allows to realize really the simplest possible Weyl semimetal, which only contains a pair of nodes, one right-handed and one left-handed. Okay, so this can be thought of as basically a hydrogen atom of Weyl semimetals. It's an intermediate phase again between an ordinary 3-dimensional insulator and a 3-dimensional integer quantum Hall insulator. So let me first remind you some basic facts about the integer quantum Hall effect. So integer quantum Hall effect is of course something that was originally discovered and discussed in the context of 2-dimensional systems. So in this case, if you have a 2-dimensional insulator with broken time reversal symmetry, it can be classified according to how many how many branches of chiral edge modes it has. Okay, and so in this case, if it's an insulator, well, the diagonal conductivity sigma xx is going to be 0. But then the off-diagonal conductivity sigma xy is going to be E squared over H times this number of chiral edge modes. Now, well, so of course, since that number is an integer, right, then there is really no way to go smoothly between an insulator with, let's say, sigma xy equals 0, which is a trivial 2-dimensional insulator that doesn't have any chiral edge modes, and sigma xy equals E squared over H, which corresponds to 1 chiral edge mode. right? And so the transition between an ordinary and a topological 2D insulator with broken time reversal symmetry must be sharp and must have the form of this plateau transition, where sigma xy just jumps by e squared over h as I vary some parameter, which, you know, in this case can be magnetic field or magnetization. Okay, now suppose I want to generalize this now to 3 dimensions. Well, the simplest way to generalize would be just to make a stack of such 2-dimensional insulators in the 3rd direction. Well, let's call this the z direction. Okay. So in this case, well, if these layers are weakly coupled, then well, it's basically clear that the whole conductivity of this whole 3-dimensional structure is just going to be, and let's say we are stacking topological insulators with sigma xy equals e squared over h, then it's clear that the whole conductivity of this whole structure is going to be e squared over h per period of this heterostructure, right, per d, which I can write in terms of a reciprocal lattice vector that corresponds to this superlattice as e squared over h times g divided by 2 pi, right? And so you can see already from this expression that there is a major difference from the 2-dimensional case, and the difference is that unlike in 2D, the whole conductivity involves a dimensional quantity, a wave vector. It's not just a combination of fundamental constants times a dimensionless number. And this wave vector doesn't really have to be quantized, right? A wave vector can change smoothly, and therefore in 3 dimensions, unlike in 2 dimensions, the transition between the 3-dimensional integer quantum Hall insulator, which I call simply this situation when I have a stack of weakly coupled integer 2-dimensional integer quantum Hall layers, transition to an ordinary insulator where sigma xy is equal to 0, generically must happen smoothly. There is no reason for sigma xy to jump directly from this value to 0. Okay. Simply basically for dimensional reasons. And so indeed, you know, well, what this picture shows is a particular realization of this transition that was proposed by myself and Leon Balance, which is basically a system of a multi-layer of magnetically doped topological insulators interspersed with ordinary insulator spacers. So in this system, you can really show that, let's say, if you start in the weakly coupled limit, you have an insulator where sigma xy is equal to this, and then you change in this case magnetization, reduce the magnetization in this heterostructure, and what's going to happen is that the gap is going to close at the edges of the Brillouin zone. And so a pair of Weyl points appear, and the Weyl points start moving closer together as you reduce the magnetization. And at this point, the whole conductivity becomes equal to e squared over h times this distance between the pair of Weyl nodes divided by 2 pi. Okay, so the whole conductivity is proportional to the distance between the nodes and varies smoothly. Okay. And eventually the nodes meet at the center of the Brillouin zone and annihilate, and then you get the ordinary insulator where sigma xy is equal to 0. Okay, and so this sharp plateau transition in 2 dimensions, in 3 dimensions, is replaced by this intermediate Weyl semimetal phase where the whole conductivity changes smoothly between sigma xy equals 0 and sigma xy equal e squared over h times the reciprocal lattice vector divided by 2 pi. Okay, so it generically broadens into Weyl semimetal phase, again simply for dimensional reasons, simply because of the fact that the whole conductivity is proportional to a wave vector. Okay. Okay, so this
Can I interrupt quickly? Maybe.
sure, sure.
I have a quick question. Maybe it's trivial, but so you're saying G, this wave vector, can smoothly go to zero. So that means that D, the separation goes to infinity. But then you're going back to the 2D uncoupled layers.
No. So by wave vector going to zero, I don't mean, of course, the reciprocal lattice vector going to zero. The reciprocal lattice vector is fixed, right?
Okay.
I just mean that sigma xy is proportional to a wave vector, right? And a wave vector is not something that's quantized, right?
Okay. Right. Okay. Get it. Thanks.
So that's what I mean. So okay, so this while semimetal is a topological phase, it really has a lot of some of the properties which are similar to topological insulators. In particular, there are H states which exist, and in this particular context of a integer quantum Hall transition, these H states may be thought of as basically a remnant of the chiral H states of this 3D integer quantum Hall insulator. In this case, this is really a sheet of chiral states that exists, that span the whole Brillouin zone of the surface of this three-dimensional structure. Now, what happens when the gap closes and we get a pair of Weyl nodes is that the H states now exist only, they don't span the whole Brillouin zone anymore, but they exist only in the interval between the Weyl points, and they continuously shrink as this distance between the Weyl nodes changes, and so therefore they're called Fermi arcs. Basically, this H state only exists in between the projection of the location of the Weyl points on the surface Brillouin zone. Okay, but I'm not really going to talk much about this. Now, so in addition to this,
can I interrupt? And I have maybe a naive question.
Sure.
In terms of like, I mean, maybe there's not a simple answer to this, but since this 3D topological insulator, the 3D quantum Hall effect was already studied quite early on, right, in the 80s or 90s by Komoto and Halperin and so on. Like, can you maybe, is there a reason why they didn't look at this transition back then in detail, or why is this something, or does this not occur if you don't tune it into this heterostructure? I mean, if you don't have such a more complicated heterostructure, you wouldn't be able to see that, or?
Well, in that at that time, this was really in the context of the ordinary quantum Hall effect, where it's the two-dimensional electron gas in a strong perpendicular magnetic field, right? So in this case, it's well, what you get is Landau levels, right? And then the Landau levels are going to disperse in the third direction, so it's not really easy to get this kind of insulator, right?
So when you're tilting the magnetic field, and because those things, I think they looked at, right? But you would not get anything like that.
No, yeah. So this really requires sort of the anomalous Hall effect.
Okay, right. Thanks.
To realize, yeah. Okay, so what I will be interested in is really sort of rather than these spectroscopic properties like the existence of H states, what I will be talking about mostly in this talk is the response. It's a bulk response of these systems, and this a lot of it, at least, may be described as being a consequence of something that's called chiral anomaly. Okay. Well, so chiral anomaly is a phenomenon that was originally discovered in the particle physics context, but it made its way to condensed matter partially through this work on topological semimetals. So its meaning here is really similar to what it means in the particle physics context, but it's slightly more general. And so well, the easiest way to understand what chiral anomaly is to apply, imagine applying a magnetic field, external magnetic field, in the direction connecting the nodes. So let's call this Z direction. And so we apply a magnetic field in the Z direction. So what happens in magnetic field is that the spectrum breaks up into Landau levels, which disperse in the direction of the magnetic field. And so generally, you know, these Landau levels are gonna basically repeat the dispersion of the shape of this dispersion is gonna repeat the dispersion of the Weyl semimetal without the magnetic field is just discretized, right? But the non-trivial topology is manifested here in the fact that there is a special Landau level which crosses zero, which crosses the Fermi energy at the location of the Weyl points and connects them, okay? And so, well, you can kind of already from here see why this is called anomaly. So the anomaly here is the fact that, you know, without the magnetic field, if the Fermi energy coincides with the nodes, then I have even integer number of electrons per unit cell. So some number of bands are completely filled, others are empty. So there is no Fermi surface. And the Latinger volume, I can say, is zero, right? However, once I turn on the magnetic field, we get a non-zero Latinger volume due to the fact that there is this Landau level that crosses the zero energy, right? And this extra Latinger volume is proportional to the magnetic field because the number of states in each Landau level is basically the magnetic field times the cross-sectional area of the sample divided by 2 pi times the magnetic length squared, okay? And so actually this whole conductivity that's proportional to the distance between the Weyl points, it can be shown that it can be calculated in this case as a derivative of the electron density with respect to the magnetic field, okay? And in this sense, it can be said to be basically proportional to the derivative of this extra Latinger volume with respect to the magnetic field, okay? So there is a nice connection here between the anomalous Hall effect of Weyl semimetals and the Latinger theorem that I mentioned before. Okay, and now so this kind of fractional Hall conductivity, by fractional I simply mean that a Hall conductivity that's not proportional to a reciprocal lattice vector but proportional to an arbitrary wave vector in the first Brillouin zone, which signifies the separation between the Weyl points in momentum space, such a fractional Hall conductivity in the absence of a Fermi surface, right? When the filling is even integer per unit cell and I have zero Latinger volume, so such a fractional Hall conductivity inevitably implies Weyl nodes, okay? So I can say that this anomaly inevitably implies gapless points, gapless Weyl points in the Brillouin zone. Okay. Now, okay, so in addition to this phenomenon of a fractional quote unquote Hall conductivity in the absence of a Fermi surface, there are other manifestations of the chiral anomaly in these systems, which have to do with non-equilibrium, which have to do with transport. So if I take an arbitrary electronic structure, then so in general, if I calculate an overlap between a block wave function at one value of momentum in the Brillouin zone and a block wave function at another value of momentum in the Brillouin zone, that overlap is not going to be zero, right? The block wave functions at different points in the Brillouin zone are generally not orthogonal. However, in these systems, in Weyl metals, if I calculate such an overlap between a block function at the left node and a block function at the right node, this overlap is actually 0, right? And what this signifies really is the emergence of a new conserved quantity, which is the chirality of the Weyl fermions, which I mentioned before. Okay, so really a Weyl semimetal has, in addition to total charge, which is always a conserved quantity, it generically has another conserved quantity, which is the chiral charge. Okay. And so basically, if I imagine a non-equilibrium situation in which I have different chemical potentials for the right-handed electrons and the left-handed electrons, right? So the numbers of the left-handed and the right-handed electrons should be separately conserved. Okay, modulo, of course, some scattering between the two values, which is always present due to impurities, but which, at least in theory, can be made arbitrarily small. Okay. However, so it turns out that precisely again because of the existence of this special Landau level, which connects the Weyl points, this conservation is actually violated in the presence of a linear electric and magnetic field. So basically, if in addition to this magnetic field, I also apply an electric field, which is in the same direction as the magnetic field, what's going to happen is that the electric field will accelerate the electrons, which will lead to bumping of electrons, let's say from the left-handed to the right-handed node, right, with the rate given by the product of E and B times some fundamental constants. And so the chiral charge, which is the difference between the left-handed and the right-handed, is not going to be conserved, even though the total charge, of course, is still conserved. Okay. Okay, and so it turns out that this non-conservation of the chiral charge actually leads to a number of observable phenomena. Okay, so let me describe them. So basically what this leads to is the modification of the density response of such a topological semimetal or a topological metal. So, okay, so as I mentioned, the basic property is that of a Weyl metal is that in addition to a total charge, I also have a conserved chiral charge, if I forget about the chiral anomaly for a second. Now, so if both were conserved, then both should obey independent continuity equations, which are just diffusion equations, right? So this is the diffusion equation for the total electric charge. And this is the diffusion equation for the chiral charge. And I've added some small relaxation term here to account for that scattering between the two values induced by impurities. Okay. However, it turns out that if you actually derive these equations in the presence of magnetic field, this is what they look like. These equations are coupled, and they're coupled by terms which involve first spatial derivatives with a coefficient that's proportional to the magnetic field. And so these coupling terms are basically a direct consequence of the chiral anomaly. They really arise from the contribution of these zeros Landau level. Okay. Now, and so if you just look at this equation, you can immediately tell that this is actually a very significant modification of these diffusion equations, and this is because ordinary diffusion equations contain second spatial derivatives, while these new terms are first derivatives, and first derivatives will of course always dominate second derivatives at long enough length scales. Okay, and what this leads to is propagating density modes even in the diffusive transport regime, and quasi-ballistic conductance. So let me explain how this happens. Well, I mean, we can analyze these equations very easily just by Fourier transforming, by going to Fourier space. So then, this gives a pair of just coupled algebraic equations, and I can easily find the eigenmodes of these equations. So this is what the eigenmodes look like, the frequency as a function of the wave vector. Now, if I take the wave vector to be very small, which specifically means smaller than this combination of the new transport coefficients, gamma and tau c. So if Q is very small, I can ignore this last term under the square root, and then I get two ordinary diffusion modes, right? There is a diffusion mode corresponding to the diffusion of exactly conserved chiral charge. So I omega equals dq squared. So this just describes diffusive relaxation of charge density at wave vector q. And then there is an independent mode that corresponds to diffusion of conserved chiral charge with some also finite relaxation rate even at q equals 0, again due to this impurity scattering between the two values. However, once the wave vector becomes larger than this number, then you see that what happens is that the square root becomes imaginary, okay? The expression under the square root becomes negative, so the square root becomes imaginary. What it means is that the eigenmode frequency actually develops a real part that's linear in Q, okay? And so there is a linearly dispersing gapless mode whose velocity is this coefficient gamma, which is proportional to the strength of the magnetic field, okay? This mode is, of course, damped by the usual diffusive relaxation term, but as long as Q is not too large, okay, this real part is going to dominate over the imaginary part, and you really get a propagating linearly dispersing mode, which exists in a particular interval of Q that's determined basically by the magnetic field and by this chiral charge relaxation time, okay? And so the existence of such a new propagating mode in the diffusive transport regime in weak magnetic fields is really a qualitatively new feature of topological metals, okay? Now, observing this mode directly may be difficult, but it actually there are closely related phenomena that are manifested in DC transport, okay? And so we can see this again just by examining these equations. So if I look at the first equation here, which is the equation for the total electric charge, it's exactly conserved, and therefore the right-hand side of this equation has to have the form of minus divergence of the electric current. So I can immediately read off an expression for the electric current from the right-hand side here. And so it will have the following form. And so you see that this phenomenon of chiral anomaly basically modifies the Ohm's law, right? So in addition to the usual Ohm's law piece, so the current being proportional to the electric field or the gradient of the electrochemical potential, there is an additional piece that's proportional to chiral electrochemical potential, which is just the difference between the chemical potential of the right-handed and the left-handed electrons and the magnetic field through this coefficient gamma. And so the interesting thing is that the second term is non-dissipative, right? So I mean, if I look at the standard Ohm's law, right? So the current is odd under time reversal, while the electric field is even. So how can this be? Well, the resolution is that basically this standard Ohm's law describes irreversible randomization of momentum, right? This is why this conductivity is proportional to the momentum relaxation time. And so this is a dissipative process. And so there is really no reason to expect time reversal symmetry here. However, the second term, this really connects a quantity that's odd on the time reversal and another quantity that's odd on the time reversal. And so in this sense, this describes a non-dissipative contribution to transport, okay? Which is a consequence of the chiral anomaly. And so what this leads to is anisotropic magnetoresistance. Okay, so
can I ask a quick question before you go?
Sure, sure.
So how would you? So it seems like the second term requires the chemical potential to be different at the two for the two nodes, right? This
Right.
is like, how would you do that? So you want to pump them selectively somehow?
No. So this happens automatically, right?
Okay.
If I pass a current in the presence of magnetic field, from the second one of these equations, it basically follows that you get this chiral chemical potential difference. Yeah.
Okay, so this is already like, but it's also proportional to B then, or is this then a
That's
B
right.
squared?
So,
okay, so
what it means is that So what it means is that basically the actual contribution to the current here is going to be proportional to B squared rather than B, because that mu C itself only arises in the presence of B.
Okay, but it's still odd on the time reversal, or?
Well, so if I so mu C, of course, itself is even on the time reversal, right? It's going to be proportional to the magnitude of the magnetic field.
Okay, it doesn't depend on the. Okay, sure.
Right.
Thanks.
So what this leads to is anisotropic magnetoresistance, basically. So I can look at let's say I have current in my sample in the x direction, and the magnetic field is in the xy plane, but at some angle to the current, and so then I will get the resistivity tensor is going to get a contribution that depends on this angle. So it generally, for geometric reasons, basically you get a negative contribution to rho xx, which is proportional to cosine squared of this angle, and then something that's called planar Hall effect, which is going to be proportional to the sine of twice that angle with the same magnitude. Okay. Now, so in principle, anisotropic magnetoresistance is nothing unusual. So any ferromagnet is going to have anisotropic magnetoresistance. However, there is an important difference here. In a ferromagnet, AMR depends on the angle between the current and the direction of the magnetization. Here, this effect actually does not require magnetization. So even though I've been really talking about a magnetic Weyl semimetal here, but the same effect will exist in a non-magnetic Weyl semimetal, and even in the Dirac semimetal. And really, it's the angle between the current and the applied magnetic field that matters here. And the second thing is that the magnitude of this anisotropic magnetoresistance in topological semimetals is really much larger than in ferromagnets. So in ferromagnets, it's typically very small, but so the largest value of AMR in a ferromagnetic metal that I could find is 50% in this exotic heavy metal ferromagnet. But even in currently existing materials which are far from ideal, like sodium-3 bismuth, this phenomenon was observed to be several 100%. Okay, and hopefully in the future, when materials which are closer to this ideal limit, where you just have, let's say, a pair of Weyl nodes right at the Fermi energy are found, this effect is only limited by the magnitude of this effect is only limited by this chiral relaxation time tau c, and so it can be very large. Okay. And so these are really new quantum transport phenomena, which can be very large in magnitude, and which can exist potentially even at room temperature, because they are they result from the properties of the band structure. Okay. Now, so in addition to this, to the DC phenomena, there are also phenomena in optics, new phenomena in optics, in particular. So in a regular metal, you know that the frequency dependence of the conductivity has the form of a Drude peak, whose width is basically determined by the momentum relaxation time tau. It turns out that in a topological metal, what you get is once you turn on a magnetic field, you will get an extra peak in the optical conductivity growing on top of the Drude peak, whose width is determined by the chirality relaxation time rather than the momentum relaxation time. And since that time can be much longer, you will get a narrow peak. Okay. And so this effect actually may have been observed already again in a Dirac semimetal cadmium-3 arsenide 2 by Peter Armitage. Okay, so do I have a few more minutes?
Sure, you can take like a few more minutes. I can ask you a few questions. So maybe 5 or so. Yeah.
Sure. Yeah. So in the remaining few minutes, let me now talk about more exotic phenomena which have not yet been observed, but which can in principle arise in strongly interacting topological metals. Okay. So what I discussed so far is in particular that the chiral anomaly inevitably implies Weyl nodes in case of weak electron-electron interactions. Okay, so a question one can ask is, does this remain true when interactions are not weak? Or in other words, I can ask, can I gap out the Weyl nodes while preserving the chiral anomaly? So in particular, while preserving this fractional Hall conductivity that's not proportional to a reciprocal lattice vector, and while not breaking any symmetry. So why is this condition of not breaking any symmetry is important? Because of course, if I take a Weyl semimetal, these two separated nodes, I can always hybridize them if I induce a charge density wave at exactly this wave vector that connects the nodes, and then once they hybridize, a gap will open, right? So I don't want to do that. I don't want to break a symmetry, and you know, in that case, you just go back to the just the ordinary three-dimensional integer quantum Hall insulator, because that separation between the nodes, once they're hybridized, this simply becomes the new reciprocal lattice vector that corresponds to the charge density wave which you have induced. Okay. And so it turns out that we can indeed quote unquote defeat the chiral anomaly in this case, but only at the cost of fractionalizing electrons and inducing a very interesting state that can be thought of as a three-dimensional analog of the fractional quantum Hall effect. Okay, so let me very briefly describe how we arrive at this conclusion. So the method that we used is called vortex condensation. So basically the procedure is that I imagine inducing a fully gapped superconductivity in a Weyl semimetal, and then I want to destroy the superconducting coherence by condensing vortices while keeping the pairing gap. Okay, so this produces an insulator because there are no single fermion excitations, because there is a pairing gap, but there is also no superconducting coherence because I've condensed vortices, meaning that the phase fluctuates strongly. So, you know, this is for the condensed matter people in the audience. This is the kind of the analog of the superconductor to insulator transition, which has been observed in thin amorphous films in a perpendicular magnetic field. Okay. And so it turns out that this chiral anomaly places actually restrictions on this procedure and always prohibits a simple insulator. but allows an insulator with a particular type of topological order that leads to this fractional quantum Hall effect. Okay. Okay. So the first thing we have to start from is the BCS superconductor, right? And so there are actually two types of superconducting states that we can imagine in this system. One is the standard BCS superconductor. So I pair states at momentum k and minus k, and we spin up and spin down. Okay, so this means that the pairing is between the two values. So I can call this internodal pairing, right? And the other one is basically a type of full differential Arkin-Ovchinnikov superconductivity, where I pair states on the opposite side of each Weyl node independently. Okay, and this is FFLO because the Cooper pair in this case is going to carry a finite momentum, which is just the momentum of the corresponding Weyl node. Okay. Now it turns out that the simplest, the most natural BCS pairing actually cannot open a gap in this system, and the reason for that is very simple. So basically, the only way to open a gap here is to mix the left-handed electrons and the right-handed electrons. Okay, but the BCS wave function does not do that, right? Because it's going to mix, let's say, electrons near the left-handed node and holes near the right-handed node, but the particle hole transformation also flips the sign of the chirality. So effectively, you are mixing left-handed with left-handed electrons and right-handed with right-handed, and this cannot open a gap. So the BCS superconductor is always gapless, so that's not what we want. Now FFLO, in contrast, does open a gap, but it generically breaks translational symmetry, right? Because the Cooper pairs carry finite momentum, and that's not what I want to do. So, but there is a very interesting subtlety here that gives us a way out. So the subtlety is the following. So imagine, so let's say that the nodes are at momenta q and minus q, okay? So the FFLO order parameter, delta of q, let's say near this node, clearly carries momentum 2q, right? However, the superconducting order parameter by itself is not gauge invariant, okay? So a gauge invariant quantity which can be proportional to a density modulation is actually something like delta complex conjugate of minus q times delta of q, and this carries momentum 4q. What it means is that when 2q, when the separation between the Weyl points is exactly half a reciprocal lattice vector, or half the extent of the brilliant zone in this direction, the FFLO will actually not break translational symmetry because 4q is going to be equal to just a reciprocal lattice vector. Okay, so the FFLO state does not break translational symmetry when the Weyl node separation is exactly half the extent of the brilliant zone. Okay, and so let me then focus on this specific state. Now, so another way to see that this separation is special is to recall that the non-superconducting Weyl semimetal has a Fermi arc that connects the two nodes. Of course, when you open a gap, you cannot just leave this Fermi arc hanging, ending at a particular non-trivial momentum in the brilliant zone. So what happens then is actually that in the superconducting state is that the Fermi arc becomes a Majorana arc, or becomes a Majorana surface state, right? And since Majorana is half of an electron, right, the length of the Majorana state in the z direction has to be exactly twice the length of the Fermi arc. And so when the separation between the Weyl nodes is exactly half the size of the brilliant zone, the Majorana state actually spans the whole brilliant zone, and then there is no problem with opening the gap. So that's another way to see that this Weyl node separation of exactly half the size of the brilliant zone is special. Okay, so now we need to condense vortices, and what makes this non-trivial is the fact that basically you can show that the superconducting vortices will generally carry Majorana modes inside, and that's a direct consequence actually of the existence of this Majorana mode at the edge, right? Because you can think of the vortex as basically a hole in the sample, okay? And so the elementary superconducting vortex, which is vortex with flux hc over 2e, okay, is going to carry a single Majorana mode that's going to cross zero at the location of the Weyl points. And so these kind of vortices cannot be condensed, right? Because they are not bosons, they carry a Majorana mode inside. So if you proliferate such vortices, you're not going to get an insulator. Okay. So any even number, however, of Majorana vortex modes, and the number of Majorana modes is actually just equal to the vorticity. So any even number of Majorana modes can be recombined into one-dimensional Weyl fermion modes, and these are genetically gapped out by superconducting pairing. So if I have an even number of, if I have vortices with flux that's equal to even number of superconducting flux quanta, they do not carry Majorana modes, okay? And so the simplest such vortex would be the HC over E vortex, okay? But that actually turns out to still, you still cannot condense that, and this follows from the fact that the insulating state that we want to obtain must preserve by construction the chiral anomaly, namely the Hall conductivity, which in this case, at the separation of Weyl points equal half the brilliant zone, is going to be exactly half a conductivity quantum per atomic plane. So it's 1 over 4 pi in units when h bar equals c equals c equals 1. Okay. And so actually such a vortex, it just follows from the fact that there is this non-zero Hall conductivity. Such a vortex will always induce a charge when it intersects an atomic plane that's equal to half the charge of the electron. And one can easily show that a pair of such charges are gonna be semimetals. Okay, so again, they are not bosons and therefore cannot be condensed. So it turns out that the smallest vortex that can be condensed is actually a quadruple vortex. So a vortex with flux 2hc over E, or 4 pi in units where h bar equals c equals c equals 1. And so if we condense such quadruple vortices, we get an insulating state that nevertheless has a fractionally quantized Hall conductivity. It's Hall conductivity of E squared over 2h per atomic plane, or it's E squared over h times half a reciprocal lattice vector. Okay. And so, well, the experimentally observable prediction would be something like this. So this is the picture of a non-interacting, of a weakly interacting Weyl semimetal, and the evolution of the Hall conductivity with the magnetization, so that I've already shown. So you get smooth evolution of the magnetization of the Hall conductivity with the magnetization. If this strongly correlated insulating state is realized, what you will see is that this smooth evolution is going to be interrupted by a plateau in the Hall conductivity, where the value of the Hall conductivity is exactly half of this integer value, which is E squared over h times the reciprocal lattice vector. Okay, and so in this sense, it's really a generalization of the fractional quantum Hall effect to 3 dimensions. Okay. Okay. So since I'm out of time, let me stop here. So this is the conclusions. So what I've shown you is that topological metal is a bulk metal, which exists for topological rather than electron filling reasons. So in a particular type of topological metal, the Weyl semimetal, those are bands at the Fermi energy touch at an even number of nodes which behave as chiral Weyl fermions. And so these nodes are topological objects which lead to observable phenomena. So fermi are surface states, giant anisotropic magnetoresistance, non-Drude optical conductivity, and even possibly this three-dimensional fractional quantum Hall effect. So thank you.
Thanks a lot. This was thanks a lot, Anton. This was a very interesting and comprehensive talk about Weyl semimetals. We have a few questions that people posed here in the chat box. Let me try to unmute, ask them to unmute so they can ask the question themselves. Let's maybe start with Jifei. I just need to find you in this list of people. Otherwise, I'm going to ask you a question. But
can I unmute?
Oh, you can do that already. That's great. I thought you have to do that. Great. Go ahead.
Thanks for the excellent talk. So I just have one question about the optical conductivity part. So, so the extra Drude peak appears, yeah, that's quite interesting. I'm just asking, what is this ZZ? Is this Z direction the same direction?
Right. So this is just the same. This is longitudinal magnetic conductivity, right? So
okay,
the magnetic field is in the Z direction, and the current is along the magnetic field. Yes.
I see. So
there is a positive magnetic conductivity. In this case, in the limit of zero frequency, but so at finite frequency, there is this peak with a width that's related to the chirality relaxation time, or chirality relaxation rate.
So could you please go to the next slide?
Oh, this one?
Yeah, this one. What's this extra peak at a point?
Well, right. So the extra peak, as far as I understand, this is due to phonons. Now,
oh, I see. Okay.
So
okay.
according to Peter.
Okay. Thank you.
Thanks. There was another question from Bokun. Maybe I just asked it here. So for Z2 invariants of topological insulators, are there any consequences on the bulk properties, or are there mostly the surface states that are interesting? If you
well, I mean, yeah. So the only observable effect of this Z2 invariant is really the surface states. Now, well, you can say that there are optical phenomena like the Kerr rotation that have been predicted to arise from the bulk physics, but I think really this is still the effect of the surface. So no. The answer is that really the only observable consequence of the Z2 topological invariant is really the surface states and whatever the physics, the response that's associated with this Dirac surface states.
But if you would gap out all the surfaces, wouldn't you get like a magnetoelectric coupling, or I mean,
well, right,
already so like built in?
That's what I mean by response, right? So
right.
One type of response would be opening a small gap, and then you get so magnetoelectric response, or Hall conductivity.
Right.
Yeah.
Thanks. Yeah, these were all the questions in the chat. Does anybody else have a question now from after? This was posed during the talk. Is there any question from? I know we have a little bit over time, but are there any other questions? I have one more question. Maybe I can go, and then people can still think about. We can ask like 2 more questions. So my question is, I mean, you talked about this new ballistic mode, and you said it's difficult to measure. But if you let's say you have an ideal measurement, or what would you have to do in order to observe it in a measurement? I mean, why do you say it's difficult, or what would you have to do in order to see that?
Right. It's not really clear what one would have to do, I guess. Well, first of all, so as I said, this exists in a particular range of wave vectors. So what this means in practice, I guess, is that, well, one way to observe this would be to actually make a sample with size that falls in between these ranges, right? And then, well, so So this is really a collective density mode, although this does not arise from electron-electron interactions. This really arises from this diffusive transport, right? So, of course, they will always be, in addition to this, there will always be modes that arise from electron-electron interactions, the plasmon, right? And so this will exist in addition to the plasma mode. Now, if you really have a Weyl semimetal with the Fermi energy exactly coinciding with the nodes, the plasma mode itself will have a frequency that's proportional to the magnetic field, okay? Although it's not going to be linearly dispersing. So then you would measure that plasmon and in addition this mode.
Okay. So you would measure, would you couple with, and you need a finite Q probe somehow, right? So optically it's going to be difficult. So you want to do...
Right, so you need a finite Q probe.
Neutrons, would it couple to this one, or?
Yeah, I don't really know. I don't think there is an easy way to directly measure that mode.
All right.
So, but you know, this DC transport phenomena and also the appearance of the peak in the optical conductivity are sort of indirect consequences of the existence of this mode, especially the peak in the optical conductivity.
Right.
Because you know what this extra peak is showing you is that in magnetic field you open up another conduction channel.
Right.
Okay.
Thanks. There is another question from Milan. Maybe you want to ask the question yourself, or I think you can unmute yourself.
Hi, yeah, thanks for the talk. So my question was about FFLO state that you get and you need it for this superconductor that still preserves chiral anomaly and stuff. So how would you induce such a state, such pairing?
Right. So you know, this is really just a theoretical tool which is needed, which we use to access the insulating state, right? So we don't really need to induce an FFLO superconductor, but you know, in principle, if you are thinking about superconductivity in this Weyl metal, you know, in principle, superconductivity, of course, exists almost in any metal at low enough temperatures. Well, with the exception of magnetic ones, magnetism may interfere, right? Now, normally, I would expect actually the BCS state to win, right? And the reason would be that in case of the BCS pairing, you are actually pairing states which are related by an exact symmetry. So in this particular case, this exact symmetry would be inversion symmetry. I mean, time reversal is broken here since I only have two nodes, but if inversion is still there, this state and this state are related by inversion symmetry. In the case of FFLO, there is no such exact symmetry, right? Even though the dispersion looks symmetric around the Weyl node, this only exists at low energies. Okay? However, what goes in favor of FFLO state is the fact that it's fully gapped, unlike the BCS state, which is not fully gapped. Okay. So, you know, which state is going to be realized really depends on details here. But for us, as I said, this is just a purely theoretical tool, right? I can always imagine that, I just imagine that I start from the FFLO state and then disorder the phase. This allows me simply to describe that insulator that does not break translational symmetry. So what I really want, in other words, what I really want in the experiment is no superconductivity, just a Weyl semimetal with strong repulsive electron-electron interactions.
I see. So this is just a tool to get the insulating state with fractional quantum Hall response.
Yeah. You know, I could actually play the same game with charge density wave. I can, you know, induce charge density wave and imagine disordering that. So proliferating domain walls in the charge density wave, you would arrive at the same conclusion, but the superconductor is simpler.
Okay, I see.
Okay, thanks.
Thanks. Yeah. So I think we had a couple of questions. If there is a final one, but I think does anybody else has a question? Please just unmute yourself in that case. Well, that seems not to be the case. So yeah. So then I think let me conclude and let me thank our speaker, Professor Burkov, again for this great talk, and thanks for entertaining us Monday evening. And I hope you'll be able to visit us in person later, maybe in 1 year or something like this. Yeah, thanks a lot for taking the time also to meet with the students and postdocs before that.
Sure. Yeah, thank you for inviting me, and I'll certainly be happy to visit in person.
Wonderful.
Right.
Okay, thanks a lot then. Goodbye, everybody.
See you.
Thanks. Bye.